Hello, welcome to the channel. What I'm trying to do in this channel is to really just document what I'm doing in terms of playing with electronics as my hobby. This is something I used to do a lot when I was younger, a lot younger, and it's something that I'm coming back to now. So over the last few years, I've done a few bits and pieces playing with things like Raspberry Pis and Arduinos, but not done anything too exciting or serious with it, largely because I've not had the tools to do it. So I've got the basics. So I have a reasonably good multimeter, actually a very nice one. I have a passably good soldering iron, which I will replace at some point, but for the moment it's doing a good enough job. But that's about it really. So I've been thinking about getting a little more serious, and the sorts of things that I'm interested in are predominantly going to be audio applications. I play guitar, so a lot with guitar effects pedals. A little bit with amplifiers, maybe, and maybe some other stuff as well. So what I'm trying to do is basically put together the kit that I'll need to do that, and to do that on a budget, because I'm not prepared just for a hobby to fork out hundreds of pounds on things like Rigol oscilloscopes and so on. So as I said, I used to do this a lot. When I was younger, I used to be able to use my dad's multimeters and his oscilloscope. But these days, things have changed dramatically. I think my dad's oscilloscope was one that he got as army surplus shortly after the Second World War. It works incredibly well, but it was big and bulky and yeah, probably about the size of the desk that I'm sitting at. It took up a lot of space. So what I have done fairly recently, which I didn't document, is to buy one of these things. So this is a DSO138. You can get these from a whole load of suppliers. You can get them as cheap as about £10 on AliExpress. This came as a kit, and I built it and it didn't work. And then I reflowed a lot of the joints and it still didn't work. And eventually tracked down one of the capacitors, which was bad. It was this one here, which is supposed to be 100 microfarads. The part that was sent was 50 microfarads and was not performing very well. So getting rid of that and putting a new capacitor in there seems to have sorted this out. So it's all very well being able to do that and to test something like this, but you've got to really know whether this is actually performing as well as it can and as well as you need it to for the tasks that you've got for it. So one way you can test this is using its internal oscillator. So I'm just setting this down to being running at 1 kilohertz and put it into a time base that we can actually see the waves. So if I connect the signal lead up to this little loop here, that's the output of the inbuilt oscilloscope, and you can see there's quite a nice square wave on there. And it's reasonably good. A little bit of rounding at the on the rising and falling edges of the wave, but actually not too bad. I should be able to tune that out. It doesn't seem to, just by tuning this little trim capacitor here. It doesn't seem to have a huge effect, but that's okay. That looks reasonably good. Where you have some issues with this is if you increase this frequency. quite a bit and then zoom in, you see that rounding gets worse the higher the frequency goes. Missed it. So by the time you get up to say 20 kilohertz, which admittedly is at the top of the sort of audio range, this is looking a bit dodgy. The question I have though with this is the square wave looking dodgy because the oscilloscope's not right, or because the signal generator that's built into the oscilloscope is not giving me good effective fast rise and fall on that square wave? And how would it look with other waveforms? So the classic answer to this is you buy yourself a function generator or a waveform generator that lets you generate arbitrary waveforms so that you can test your oscilloscope and see how good it looks. You still have the issue that if there is a problem, you don't know whether it's the signal generator or the oscilloscope, but you can then check those against other sources if you need to, if there's a discrepancy between them. And hopefully you should be able to pin down what the issues are. I am well aware that a £10 oscilloscope kit is never going to give the same results that a £400 Rigol is going to give. And that's fine. It just needs to be good enough for what I'm doing for the majority of the time. So I will just quickly put the time base back up and drop this down to 1 kilohertz again. There we go. And we'll have a look at the signal generator that I bought. So this I bought as a kit, took a little while to get it going, but it's fine now, it works. On the other hand, this is the signal generator that I went for. So this is one of the bog standard ones that you can get just off Amazon or eBay or AliExpress. They cost a few pounds, £5 or £6. And this one came built, so I didn't even have to do anything to it. So this is based on this XR2206 chip. And it's not all of that complicated. It's basically enough support circuitry there to get the chip to work, to change the capacitance value on the timing capacitor, so you can set a frequency range and then use the potentiometers here to fine-tune the frequency that you want. And then this affects the amplitude, or if you look really carefully at the board, the amplitude. Maybe that's the attention to detail that I should have started to worry about when I looked at this. Anyway, we can just very quickly hook it up. I'll just bring the multimeter back in and find the that's that one. There we go. So this is a 12-volt power supply. Set this to DC volts, you can see that clearly enough. So this should be center positive and it should be 12 volts. There we go, 12.626 volts. So that's exactly what we need for the board. So I can plug that in there. And we can hook this up to the oscilloscope and see whether we get anything sensible out of it. So there we go. Unhook that square wave. So this is set to the middle capacitance value, which should give us a range of 100 Hertz to 3 kilohertz. So it should look fairly similar to what we saw before. If we look, well, we're looking at this triangle wave at the moment, but we can't really see anything. I can change the amplitude, it has no effect. I can fiddle with the timing resistors to change the, and we see basically nothing on the oscilloscope at all. It's flatlining. So it looks like there's an issue with this board, and we need to get it checked to see what the problem is, and then see how we can actually fix it. So if we have a look quickly at the schematic for this board. So this is the schematic that was sent with the board itself. It's a fairly poor scan. I've cleaned it up as much as I can, but it is not massively readable. So what I've done is I've taken that schematic and I have redrawn that in KiCad, so you can actually get a better view of what's going on with this circuit. So at the centre of the circuit you can see the chip that's labelled as XR2206, and this apparently is how it's all set up. If you look actually at the board, you can see J1, the set of jumpers there that are used to select the capacitor. It apparently only has 4 settings and the 5th one's not connected. That is not the way it's actually wired in the board. So those 5 capacitors are set individually selectable. Those last 2 are not wired in parallel. But that's the way it's drawn on the original schematic. So these 2 down here, C7 and C8 at the bottom. So when you actually look at what's present on the board, so you have at the bottom left around J1, you have that set of 5 capacitors that you can select. And all that does is let you switch between one of those capacitors between pins 5 and 6. Pin 7 goes to a resistor, or a variable resistor in this case, or a series of variable resistors that let you tune the frequency, whereas the capacitor lets you set the range. Up here you have a couple of capacitors that are filtering any noise out of the input power, and then you have a voltage divider R3 and R5, which supplies half the VCC to a variable resistor that's used to set the amplitude of the triangle and sine waves. There's the sine wave output, and on the right hand side you just have a switch, which is implemented as a jumper on the board because it's presumably cheaper. So when that switch is open, the chip will produce a triangle wave. When it is closed, it will produce a sine wave. And that's essentially it. So there's nothing on there that's too exciting. There are no discrete components. There isn't even a diode to protect against reverse current, or there are no transistors, no op amps, nothing complicated there at all. It's just a set of discrete components. So that's fine. There are some things up here which aren't connected. Now, if you look around on YouTube and the rest of the web, you'll find lots of other videos about this chip and about these function generators, and basically when they work, they seem to work reasonably well. Roger at Klinker Labs did a really good analysis of this circuit and basically showed that some of these features don't work that are on the chip, and some do. In particular, the 2 pins 15 and 16, which are labelled as Sim A1 and Sim A2, should let you change the symmetry of the waveform that's output. So those are not connected at all in this circuit. If you wanted to improve this schematic, you certainly could by adding a few more components in, really not very much. Changing the R4 from a fixed value resistor to a variable one will let you tune the total harmonic distortion of the waveform. And if those pins 15 and 16 are implemented and work on the chip that you've got, that should let you change the symmetry of the wave. So change your triangle wave into a sawtooth, for example. But that's not something that we need to worry about with this. So really what we want to do with this is get the chip to function in the simplest circuit that we possibly can, which will let us basically see if it's going to work or not, ever. So if we strip away everything that you don't need from that circuit, you will get a circuit that looks a little bit like this. So we still have the power filtering with the two capacitors on the left, the voltage divider and the variable resistor for the amplitude control going into pin 3. We have a single timing capacitor across 5 and 6, which I've gone for the middle range, which should give us a frequency range of 100 hertz to 3 kilohertz. And then we have a variable resistor between pin 7 and ground that will allow us to tune the frequency. And that is essentially it. That is basically all you need to actually get the chip to run, in theory. So what we can do is we can pop that onto a breadboard. So this is the circuit that I've just shown on the schematic, actually built onto a breadboard. So you can see, well, let's actually check these. Again, the power supply, still 12.26 volts, exactly what we had hoped. We can connect that onto the breadboard, and we now can see that the 12.62 volts is across the hopefully across the smoothing capacitors. If we look between earth and the voltage divider, you can see that's 6.128 volts. Can you see that? Which is half the supply voltage, so that's working fine. Output from that goes to this potentiometer, which is the amplitude potentiometer, which is connected to what will be pin 3. Pin 2 is the sine or triangle wave output. Pin 1 is connected to VCC. To ground. Pin 4 is connected to VCC. This is the timing capacitor, which you can't really see there. There you go. Which is between pins 5 and 6. And then pin 7 is connected to the output of the timing resistor. This is the square wave output on pin 11, and then that bridges pins 9 and 10 and 12 and to ground for the bias. So that's all we need. We've not connected up with pins 13, 14, 15 or 16. We shouldn't really need them. So I'll just quickly disconnect the power again. And we can pop out the chip from the board. Fortunately, it's socketed. Make it a little bit easier. And then we should be able to get that in just there. So really quickly check that pin 3 is connected to the amplitude control, pin 4 is VCC, yeah, that all looks fine. So now if we push the power back on, we can turn the multimeter off and we can connect. This line is ground, so connect that to the black alligator plug. That looks a bit odd, but there you go. And this should be the sine and triangle wave output. We connect those, and the oscilloscope is showing us nothing. There is nothing there. We can up the sensitivity, but essentially we don't have any signal there to speak of at all. We're measuring about 0.1 peak to peak in the noise, which is probably mostly coming from the power supply still. So I think that shows fairly conclusively that we have two circuits, one produced in a lab on a PCB, one produced by me on a breadboard. And when you put the chip into either of those circuits, nothing comes out. So I think we can be fairly confident that this chip is completely fried. And it's never going to produce anything useful ever. So, okay. So is this worth it? Well, not at the moment. There's not an awful lot on that board that's actually useful beside the chip. But I still do need a function generator. I still want to see something on this oscilloscope rather than a 1 kilohertz square wave. So there's a number of options here, I think, and I think the one I'm going to go with is probably to buy another chip. So I will order another chip from wherever I can find one. A lot of the videos that talk about this chip say that these are cheap Chinese clones of the chip. I don't think that's really fair because the chip's effectively obsolete. XR don't produce them anymore. Nobody else does that I can see, apart from maybe a few Chinese chip foundries. I'll probably have to get one from AliExpress, and we can see what that looks like. Again, we will see then whether the other parts of the chip, for example, around pins 13 to 16, see if we can actually tune the total harmonic distortion, see if we can actually change the symmetry of the wave on there, but we'll see how that looks when we actually get it working. In the meantime, though, I still do need to sort something out, so I will look at other alternatives as well. So that's it for this video. We'll leave it at that. As soon as I get something in from AliExpress, then I will drop it into the breadboard and see how well it's working, and upload that, I think, as the next video. So thanks very much for listening and watching. If you want more information, I put links in the description to a web page that will show all of the schematics. I have also linked to Roger from Kainco Labs, his videos on this as well as, and I put a couple of links in for the places where I actually bought these. If you want to buy yourself a broken signal generator, most people seem to be fine. I seem to have been unlucky. But yeah, until the next video, that's it, and thanks again for watching.